Trying to connect to this Wi-Fi.
Lunch is always a little off, but I think it's time. So, if you haven't turned in your homework, just wait till after class. As usual, I'll be nice and give you the 5 if you feel like you can. Slip it under my door. I have to go run to Kmart after class for no reason, and so slip it under my door. I'll be nice to you at 5. At 5, I have a meeting, so at that point, I'll upload the answer key. I have not written your present problem set, so it will be done late tonight. Sorry about that. Again, that subject that I didn't get to cover, it's always throwing me off in a big way. That curriculum thing. Sorry about that. But, okay, so again, problem set will be posted late tonight. It's your last problem set before the exam. Other class news. Oh, the scores on the homework were pretty much the same as last time. 93%. Extraordinarily high. So I'll just curve it an extra 10. Gets you down to, no, I'm just kidding. No, I'm totally comfortable with the questions. These are very similar questions, not the same, but very similar to those I always ask. You all get A's, you all get A's. I've got no problem with that. When I get in trouble for it, which I will, you don't care. When I get in trouble for it, there will probably be questions about this. I'm just simply going to show them copies of your tests and say, look, these are pretty reasonably hard tests. And also, remember I told you I do that. I know what my doppelgangers, the other B's at Northwestern, North Carolina, MIT even, because I was there, I know what kind of questions they ask. You're getting the same ones. So I'm not harder, I'm not easier as any of them. So I'm very comfortable with your grade. Okay, testing 2 Fridays from now. Bloody likely a double lecture on Friday, so that we can review Wednesday. Sorry about that, but it's fair. Oh, I need to send a doodle poll, but I know you wanted, it's very obvious you want to review, what is it? Oh, next Wednesday, right?
Yeah.
Next Wednesday's a review, exams on Friday. So, don't much have to say. Oh, one other bit of class news. I did notice right before class, I am about exactly 1 day behind the syllabus. Of course, the test will be adjusted for that fact. So, anyway, so if you are reading, which you probably figured out you don't need to, I'm okay with that. So what? I don't know that I'm going to catch up. I doubt I'm going to catch up. So whatever you see is the last subject, and I don't quite remember what that is. Before the test, I don't think I'm going to get to there. But of course, the test will reflect it. Don't worry about that. I don't give you old tests. That doesn't happen. So I know where you're at. Okay, I'm blabbering on and on. I need to go ahead and get started because I do have your homework to get back, so I'll be a few minutes early. I know last time I wasted a lot of time on depressing stories, but I don't think Wednesday's going to be depressing story day, so no depressing stories for today. And we will end early to get your stuff back. Remember, again, we're now in our 3rd week. Hopefully you've reviewed your notes from head to toe at least once. Next week you should have it done twice. Remember that bit? And remember, look at your homeworks. See which ones you didn't do right. Look at the answer key, then try to do it again and watch yourself make the same mistake. I swear to God you will. And then you're going to do it on the test. And that's the B student. The A student will repeat the question one more time, get it right, and then they fix what was wrong up here, and when they're at the test, it's still fixed. So, okay, anyway, I'm blabbering on. Here's a review what we did last time. Adiabatic. Adiabatic is thermally insulated. Let me put it this way. Again, for the review, I did this a slightly different way. You don't have to write this down. We have adiabatic transitions. We have isothermal. We have 2 paths: reversible, irreversible. Okay, and I mentioned to you that we had ways of connecting these together that were like this. Adiabatic reversible, adiabatic irreversible, isothermal reversible, isothermal irreversible. We started out with isothermal, which I hope you at this point think that that's pretty easy, especially now that we're on the adiabatic. Big picture though, these are limiting forms. These are like the most extreme ways you could do things, where some things are perfect, like isothermal, no temperature change whatsoever. That means U is 0, H is 0. Kind of an extreme condition. Adiabatic, 0 heat transfer outside and none escapes either. Not very realistic. Now, again, I want you to realize these are extrema. Things are in between. Things can't be in between. And that actually was your last homework. Notice that question 4, I'm not giving answers because I know I don't have all your homework, so I'm not giving answers. Number 4, you had heated a gas inside of the turbine. Now, if it's going to stay at 600 degrees, it has to be wrapped in glass wool, right? So that made it adiabatic. Now, hold on one second, people. How could I have heated it if it was wrapped in glass wool? How could I have done that? Now, my point there is, it wasn't a fully adiabatic question. It wasn't really, it was somewhere in here, but not on the 4 corners. So that question required me to build a cylinder and to snake electrical wires inside of it and add a heating element. So it was adiabatic in the sense that it was glass wool, but there was a heat transaction. So I was kind of adiabatic, but kind of not either. So we do have these things that exist outside of the extrema. I'm going to mostly focus on the extrema, but I mean, of course I can heat a gas encapsulated in insulation. And there's lots of machines that do that. And notice that just because it didn't follow an extrema, you had every ability to answer the question. I said, this amount of heat went into the system. How much did the temperature change? Well, I gave you the heat capacity. I gave you the number of moles. You're done. You can answer that. You don't have to be in the extrema. Okay, today's lecture is going to also not be in one of these extrema. It's going to be very unusual. Again, but hold on, let's review a little bit more about adiabatic and extrema. And I talked about how temperature is going to change, and we're going to change volume. And I did an expansion, and expansions cool things, and of course there's a finite change in U, which I'm going to tell you a gas expands adiabatically, it's a mole, it was in a liter, and all that. And I pointed out to you that I don't know how to do this, but I can do this. I can let it expand isothermally. That's a pretty easy answer. I know that if I change the temperature at constant volume, that I have this. All right, that's the simplest thing in the world. Funny thing about adiabatic, I said this last time, but I've repeated many times. Adiabatic, remember, I said on the test, an adiabatic transition occurs with 1 mole of a blah, blah, blah. Write this down immediately. That is the definition of adiabatic. Isothermal, delta T is 0. Write that down. You just got a point. That was a very easy point to get. And it's one of the things you got to remember. Okay, heat. I like to think about how heat does things via heat capacity. Yet adiabatic, there's no heat transition, yet I calculated thermodynamic variables using heat capacity. But there's no heat. And again, remember, us chemists, that's not a very good definition. The engineers have better definitions, chemists don't. So just because the heat transaction is 0 doesn't mean the gas doesn't have some kind of heat inside it. Doesn't mean it's freezing cold inside of there. Now, last bit we did, this is again a review, you don't have to write this down. I said no matter what, okay, I'll write this down again. And no matter what, this is still going to be work. Obviously, I had a negative work in this case. And if we're going to be reversible, this is always true. Reversible. And then, now, here's the problem. Remember, I would like to just integrate these and have CV delta T minus P delta V. You can't do that because P contains V. That's not allowed. So I have to get the P, I have to get the V out of P. Oh, and I have to get the T out of P too. Well, that happens to be nRT over V. And from this, and I'm not going to do it again, it was very simple. I even did it without notes. Because, well, yeah, I've done it a billion times, that's true. We derived this. And remember, I also warned you that when you're doing an adiabatic problem, write that down first because that's just a free easy point. The next thing to go for is maybe I've hidden the number of moles very snarkily like I did on the on the last homework on that second question. Maybe I've done that, whatever. But no matter what, you want to get to the final temperature very quickly. And that is where you're going to get the rest, right? Because you're going to plug that in here to get the change in U. And then you're going to get the change in H2. And that's most of what we've done. Now, another thing to note that based on how I set this up, because you can imagine, I could give you the final temperature. I got 4 choices of what not to give you. I have to give you the rest. I have to, or that's a null question. All right, so imagine that I gave you the temperatures, or no, what would be better? I gave you the volumes and not the temperatures, which is bloody likely. Tell me, if I want to put this over here, do I just do that? Is TF over TI equal to this, to the CD over MR?
No.
No. TF over TI, sorry, I'm writing badly. TI over TF. Now I want to raise this guy to a power. Right, flip it. All right, because I may set up the question where this is easier than that. That may very well be the case. And if you get confused, if you want to bring this over here and say, wait a minute, is it that way, or you flip it, what do you do? Yeah, start plugging in random numbers, not ones or twos, and prove to yourself that if this is 1 over 3, right? Not one, don't mess with twos, right? Don't mess with ones. This is 1 over 3, and that's 3 over 1, it'll work. And again, just numbers. In case you just don't remember the identities, that's fine. Now here's another thing I can do. And I'm just doing this off the cuff because it's not that hard. I'm going to stick this, TF over TI. Now imagine I don't give you volumes, imagine I give you pressures. Okay, I can tell you that no matter what, I would have had to have given you enough to calculate the volume. In the question on, you're going to have a couple of these on the homework, all right? And you're definitely going to have it on the test. Count on it being on the test. So I can hide the volumes by giving you pressures. You know that. And I'll tell you to use the perfect gas law. But that is something I'm full well capable of doing. Giving you the volumes via pressures, not directly. Not very well likely going to do that. Now, what you could do is take this sucker and put that in terms of volumes, in terms of pressure, sorry. nRT, so that would be TI over PI over nRTF. You see what I did? Over PF. Okay, and now again, I have a hard time. 1 over 3 over 7 over 9. That's how I would try to figure out whether I'm doing this right and plug that into my calculator. But what I'm going to have is this is going to get flipped over, so I'm going to have TI over PI times PF over TF equal to that. Okay, so then what I could do is, I'm sorry for all the algebra, I'm going to bring TF over TI to the other side. Now again, this is a very easy test question because it's not hard, and it's kind of relevant. My point here is I want to show you that there's actually, unfortunately, you can cast these with any of your B's or T's or P's. You can do it with any of them, any combination. Now, if I want to, let's see how up on your math you are. Now this is workable. I don't have to do any simplification, but just to practice your math, and because I'm already behind, so I might as well slow myself down even more. X times x to the n is x to the
N plus 1.
There we go. Let's make that CV plus NR. All right, I just did a step of math in my head. I took the 1 and I made it NR over NR and I combined them. And now what have I got? What's CV plus N? I'm not writing very big in mine. Sorry.
CP.
CV plus NR is?
CP.
Right, so this is TF over TI to the heat capacity constant pressure over NR is now equal to PF over PI. Or stick with this, whatever. All right, easy questions that just are not hard at all. And remember, another big thing, big picture about adiabatic, reversible or irreversible, but I'm doing reversible right now, is that PV equals nRT. I'm gonna stick with that. I'm not gonna throw in van der Waals equation. It's too hard. It doesn't change things that much anyway, like you saw in the homework. I will work with perfect gas, so therefore I make the perfect gas law work. So why am I doing why am I doing this? Why am I doing this if I just use the perfect gas law? Because normally you relate a change in volume to a change in temperature because the pressure was held constant. Something was held constant. But here you got P, V, T changing in one equation. The equation still works, you just don't know, it's just not enough. You need like a second equation. This was just a clever way out of the problem. And that won't even be interested here. Okay, now let me point out one more thing, so that's reversible. And irreversible is going to be, let's integrate it. Irreversible, CPET is going to be minus P. Oh yeah, I did get a minus. Okay, again, easy. Easy. It looks easy, it's not. This is actually worse. And this is because I've got one equation with two things changing. It's unsolvable as it is. I can't, be missing TF and BF and then put those in one equation and come up with an answer for both, right? So I'm looking for two things at once, but I have one equation. You can't do that. Okay, the answer is simple, clever enough. Okay, this is VF minus VI, so this is going to be nRTF over PF. And of course, the final pressure will be the exterior pressure. Again, a cylinder expands because it's at 2 atmospheres of pressure. It'll expand until it's at 1 atmosphere of pressure. The exterior pressure is therefore the final pressure is of course the exterior pressure. It has to be. I could make it not that, but that's just stupid. Okay, so I've just made it a little easier. Minus the initial. Oh, and of course I have to give you the initial pressure. That is something has to give you. And I'm sorry to do this. Let me just make certain you see it. Okay, now one equation and only one unknown. Only TF is not known. Now you can solve it. However, this is kind of a calculator nightmare. I mean, can you use a calculator? You did when you were 12. I'm pretty sure you still can. It's just you're going to have to use it a lot. So here's what I just did right before class. I wrote some examples. I rewrote all of these notes very well. I still wanted you to write them. I had this written a while ago, and I was going to give it to you, but I made you write it anyway. Helps it stick. So I have all of these worked out. And when it comes to irreversible, because this is actually much harder than it looks, really is, I worked a couple of problems. So 2 handouts. As much as this doesn't look that bad, it really kind of is. And so look at the handout, follow along. Again, it's not terrible, it's just a lot of stuff in it. Notice I could have made these final volumes in the initial volumes. I could have done that too. And anyway, I have some of these on your homework. It should be more than enough for you to figure it all out. Okay, and then I've got, I've done whatever my change in volumes and temperatures. I've done Q, which was easy. Work is then U, and work is, and U is this. So I've got work, I've got U. The only thing I need is H. And how about, and then engineers will go a little bit nuts about it. I've been careful about my squiggly delta versus my capital delta. Sorry about that. It's just, it's a change. I don't worry about the symbology. And in this case, all right. So we already know that the change in U is CV delta T. And I've changed temperature. I've given you moles. So you can certainly figure this out as well. You calculated the change in temperature. However, you did it this way, or you did it this way. So you've got the change in temperature. I had to give you N. I had to give you CV. Again, you calculated the change in temperature. There you go. There's H, and that's all you have to do for now. Because we haven't gotten to entropy yet, but that's coming out on Monday. Okay. That was really just a giant review. I haven't even gotten into today's actual subject. Joule's experiment. And I want to harp back on that thing on top. We're going to step outside of the extrema. So I just did all adiabatic, reversible, irreversible. Joule did this experiment that again doesn't fit nice into those cookie cutter problems. And I'm not going to really hark on this too much on test. It will come up. It will be on the first test. I may say something about on the final, but I'm going to kind of back up. I may ask word questions. In fact, that's bloody likely what I'm going to do. But what Jewel did back in the day, he knew that he was one of the people that just started figuring out all of this stuff. And he wants to know whether it really works or not. So he gave it a test. And so actually like Einstein did this with quantum mechanics. See, Einstein didn't believe in quantum mechanics, and he's a clever guy. He didn't understand it, so he thought it was wrong. And he's actually a jerk. But so Einstein actually told the quantum people before he died, he said, I don't believe you, but let me tell you, if you ever do this experiment and you get observation A, you're wrong. If you get observation B, you're correct. They got observation B, Einstein was wrong. Okay, so in quantum mechanics worked. He never actually believed in it. So Joule does the same thing with all this thermo stuff. He says, if I've really gotten this right, I'm going to work a whacked out device and see whether I get the result that's reasonably expected. And if I do, then all this thermo stuff is right, and go sit by yourself. You may notice the answer to one of your homework questions. What he does is he builds this. Okay, this is gas cylinder. Right, a little metal bottle of gas. He attaches a valve, and he attached a bigger volume. He made the pressure 0 as well as he could. The device wasn't really all that great. Okay, then he wrapped it in glass wool and filled it with water. So there's gas in here, connected by a valve. He knows the volume. He knows the pressure. He evacuates the other one. Sometimes, remember, I told you I'm snarky about how I do things. And I may not say something's adiabatic. I may say it's wrapped in glass wool. Okay, and inside of here is water, and he has a thermometer stuck through the side. So he can measure the temperature of the water. Okay, now here was the idea. Again, you can see why this is kind of wacky, and we're going to see weird things happen with these types. And I'm going to show you one more of these kind of weird experiments that these guys did back in like 1890, 1880. What he wants to do is expand the gas into the vacuum. Do you think will the gas cool? Do you think? Yes. Yeah. Probably. Now remember, I've been saying, if you expand the gas, it'll always get cold. Depends on how you do it. All right, I was a little bit snarky about that. So maybe, maybe not, but he thinks it's going to get cool. I agree, that's probably a pretty good idea that it will. Now, the water is insulated, so the water will get cold. It'll get cold, he knows its heat capacity, he knows how much he added, he can figure out how much energy. He can figure out how much it cooled, right? That's what he wants to know. And anyway, so now, not only is this device really kind of weird, there's some other unusual things about it, but let me point out. So it's adiabatic. First thing to right, adiabatic. Okay, now I know that the change in use, the change in work. What's the change in work? How much effort does a molecule have to shoot off? So he opens the valve. This is a vacuum. Molecules just randomly happen to be going in that direction. How much energy does it take them to keep moving with nothing hitting it? Zero. Right, so there's no work. And I've gone over that a couple of times. Remember that P, if you're a graphical person, remember that P versus V curves where I showed that reversible work is the most negative? Remember, the bottom line was pressure equals 0. And so if you immediately go to pressure equals 0 and you integrate, you got no area. So anyway, work was nothing. I should write units as well. Now, what he's wanting to do is calculate the change in temperature with respect to volume. Now, I've got multivariable calculus. I'm obliged to hold something constant. What is it? Okay, the volume expanded, the pressure decreased. I don't think they're constant. I just said to you what's constant. It's right up there. Temperature probably is not going to be constant because he kind of expects it to cool. I've written that something, the change in something is 0. It's right behind me. It's, that's you, it's you. That is true that Q is 0, right. And this would be the same thing. I could say that the change, well, actually, no, I don't want to do that because remember, heat is only a change. There is no heat. I can't say Q is equal to something. I can only say the change in Q is equal to something, so that's not a good choice. It works because the change in Q is U. Anyway, whatever. All right, this is what you do. Okay, so now what we want to do, and if you're going to, let's see, how quickly can I do? No, don't have the room. So anyway, okay, our goal is to get to this. I just cut myself. And you see freaking circuit board is still writing the board. I'm not, I wrote a note, he's the only other person who uses it. I wrote a note that said, freaking Richard's born. Okay, now I told you that when we did CP minus CV, hopefully it didn't rattle your cage too bad. It wasn't, come on. Hopefully it didn't rattle your cage too bad. Remember, I'm getting to know your names. You don't have to read already, by the way. That what I want to do to get to that is, it looks like I want to start writing down the changes in the function. I'll choose U, and I want to think about how U changes as a function of certain variables. And I showed you that what you choose will matter. That when we did some examples on that last Friday, when you make these expansions, the change in U is the yada, 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 what variables you pick will either lead to reasonable solutions that inform you of what you need to know, or the change in U is the change in U, which is a null result. True, but not useful. You have to know what the correct variables are. On the test, I will point you in the right direction, because there's no good way to know what variables to choose. You pick some, you do the problem, you got a great answer, and you did it right, or you got in a tailspin, or ended up with just changing U is changing U, which isn't helpful. So I happen to know in this case that I want to expand U about T and V, because I know it's correct, because I already know. So again, on the tests, on homeworks, I'll always point you in the right direction. So if I'm going to expand about the change in volume, in temperature, well then, I have to do that. As soon as I've done that, whoa, not right. Wrong thing. They have to cancel, right? Change in U has to be equal to the change in U. Cancels. All right, I wrote constant T, so I'm obliged to do this. There, I didn't screw that up. Okay. Now here's a funny thing. What is the change in U? 0, right? So I can say this is 0. I can say this is 0 right now, and it would actually save me some steps, but I won't, because you're not going to run into that often. So what I'm going to do is pretend that I don't know that. I could save a lot of steps if I did know that, but I'm not going to let myself know that right now. All right, I'm looking back at what I'm trying to get to. dT/dV. All right, I got a dt right here. I need to get that. I need to get there. All right, so it looks like I need to divide everything by dV. And I'm almost there. I'm sorry, these guys, I'm good on give you a hard time. See what's happening. Again, I'm obliged to hold something constant. What am I going to hold constant?
U.
Right, U. Because that's what I'm trying to get to that right there. Okay, now instantly, if you were blind to it, now you're not. Clearly 0. Do it that way. Changing U at constant U, now it's very obvious it's 0, in case it wasn't before. This one's always trivial. And du dt at constant V, do you know that one? CV. Right, so we've already had that one. So we've got 0 is equal to change in U with respect to volume, constant temperature, plus CV. Change in T with respect to V at constant U, the thing I'm trying to get to. Okay, so I can already see what I'm going to do is bring this over here and divide by CV. Okay, and there we go, I'm done. Sorry, look at that. Try to make my using these different, some people always screw that up. Okay. Now, this gets a little symbol, I will never bring it up again, don't even write it down, the Joule coefficient. Sorry. Joule coefficients. I'm not going to bring it up again, but I can't tell you what your MCATs or GREs or whatever are going to do. I have no idea. So there it is. I don't memorize this, you should have figured that out about me by now. I'm not going to say what's the Joule coefficient. I'm not going to say what's this symbol. I'm not going to ask that. Okay, I'm done. I'm done. So, now here's the thing. So he did it, right? He got named after him. He did it. Guess what he got? Guess what the value of this was? 1. You're thinking of quantum, where everything's a 1 or a 0 in each bar. Okay, what did I say? If temperature is held constant, U is held constant. So if U is held constant,
Temperatures.
so this should be
0.
okay, and that's what he measured. But it's wrong. In fact, he wasn't looking for 0. And I'll explain why. If this is a perfect gas, then yes. The answer should be 0 for a perfect gas. And when he measured 0 and later fixed it, it was actually I think I have the information. 1924, I think Joule was long dead. Someone rebuilt the machine. See, he just didn't have good tools. He didn't have good thermometers. So maybe he was using a cow head, a balloon, I don't know. But he had primitive tools, so he measured 0. Now, he knew he was going to get a small number. He knew a perfect gas ought to be 0. And when he measured, when he couldn't make the measurement, he counted it a success. But he did expect a little bit of something to come out of this because gases aren't perfect, and he knew that too. Right? At this point, they can isolate pure gases, and they measure their temperature and pressure and all that jazz. They knew their volume, and the numbers just weren't perfect with PV equals nRT. So he knew that he ought to get a number, but it ought to be small, so small that he ultimately couldn't measure it. So then he assumed that everything about thermal was right. But so now, why is it not 0? Let's draw U, not changing U, as a function of volume. And because perfect gases have no volume, they don't interact, they don't hit each other. Hitting each other is bad, right? That tends to increase pressure beyond perfect gas. Whatever this gas is, I don't know, it's N2, so U is 5/2 RT. I'll just draw that, but this isn't, but even N2 is very close to a perfect gas. That's probably why he measured 0, because he probably was working with air, which is mostly N2. And that's why he measured such a small number that he couldn't actually measure, he got 0. But what real gases do? Most gases do this. And it asymptotically goes to 0. Most gases, they like each other. Okay, the other extreme is obvious, it's just a mirror. And of course, once you get to very low volumes, and of course, real gases behave like perfect gases. And of course, H2, HE, the weird ones, the only 2 weird ones. They do the opposite. And that's because they hate. They're haters. They're the gangsters of the gas community. So now, just think about this. If these things like each other, because they can induce dipoles, or it's like HCl, a very unusual gas. HCl definitely has a big dipole moment, and they love being right next to each other. But if you give them a big enough volume, they just get lost. They never see each other. And when you line up your dipoles, you're going to lower your U, which is good. Remember, it's always good to raise things up through the party, through the roof. Not when it comes to energy. Energy wants to go downhill. And actually, I'm going to explain why that is. There's actually a deep reason for that, but we are going to go over it. But things line up, that technically is good, and that means you load your energy. But when you just don't let them do it, well, your U raises, because you can't have this positive, which by positive I mean actually negative interaction that lowers your yield. Now, again, he should have seen the temperature of a water change. And then from that, he would have had to have done some more calculations, and he could have found out what these numbers are. What should he have found? Let's think of this. Let's look at most gases. And now you're going to see more and more why I'm obsessed. What am I doing? Constant T. All right, positive or negative? We're doing most gases. I'll write that down in case you forget your notes. Most gases. Look at the line. Does it go up or down?
Positive.
Right, positive. Okay, now, let's look at this thing. Okay, I've got the Joule coefficient. Joule coefficient. The TdV constant yield is equal to something that is positive. All right, CVs, are they positive or negative?
Positive.
They're always positive, there's no negative CV. I've got a minus sign making this negative. Now you see more, I mean, we're going to do a ton of this after the first test. Is it positive, is it negative? Because it's a practical thing. Okay, if volume increases, temperature does what? This is negative. V goes up, T goes right, it cools. Just like you thought it did. Now, I've been saying that a gas expands, it always gets cold. But will hydrogen and helium, when this is a negative, I got two negatives, is a positive. So if volume goes up, temperature goes what? Up. Goes up. Okay? So that means that I expanded hydrogen and helium and they got hot. I've said over and over again, you expand a gas, it gets cold, hydrogen and helium will do the opposite. However, warning, I told you we're not working in a normal regime. There are days when, does anyone's car engine works like that? Does anyone design a power plant that works like that? So if I'm doing an adiabatic equation and I compress hydrogen and helium, is the temperature going to increase or decrease?
Decrease.
Wait, what did I just say?
Compressing hydrogen or
Right, if I'm compressing hydrogen or helium, does the temperature decrease or increase?
decrease.
Increase. It increases. If I just have an adiabatic cylinder, I compress hydrogen, helium, and nitrogen, and oxygen, and every xenon, they all get hot. I have hydrogen, helium, xenon, neon, whatever, and I expand and get cold. In my metal cylinder wrapped in glass wool. That's the key. The metal cylinder wrapped in glass wool. Is this a metal cylinder wrapped in glass wool? No, it's not. That is not a metal cylinder wrapped in glass wool. I compress. How much? All right, so again, no matter what the gas, I compress, it gets hot. How much work was done? Positive work, negative work, zero work? Which one is it?
Positive.
Positive work. Compression is positive. Sorry for the engineers. It's going to be positive. How much work was done here?
None.
None. It's different. It's a different machine. The different machine returned a different result. That shouldn't surprise you, okay? So don't let this get confusing. This is why I emphasize the whole, the whole adiabatic reversible, adiabatic irreversible, isothermal, Those are extrema. We can work outside of them. And this is a bizarre little device that was built to do exactly that. And when you went to that much trouble to do exactly that, you got weird results. Again, not surprising. So just understand that. And again, the experiments were done with most of your regular gases, and they got cold, and hydrogen and helium got hot. But again, this is not your normal cylinder wrapped in glass wool. It's pretty far from it, actually. Okay, so again, we're Joule. He knew he was on the right track. He knew that he should have gotten a little tiny number, and he didn't. So he was a little perturbed, but he felt that it was actually overall good vindication because he knew that under normal conditions, most gases actually, PV equals nRT actually works pretty well. And in your homeworks, if you've noticed, power plants, methane about to liquefy, those are extreme situations, but you have to do that before you see how things really work, because deviations of P equals nRT at room temperature just aren't very big. So he teams up with Thomson. Joule Thomson. The guy whose name is misspelled more often than not, Chomp, is wrong. This guy Thomson had another name. Remember? Kelvin, Lord Kelvin. This wasn't made a lord yet because he wasn't 40 enough. Okay, so Nick can imagine that what I want to do is if I messed around with the volume and it didn't work well, what else would I want to change?
Pressure.
Right, yeah, that's obvious. And if I'm talking about, when I was talking about volume, I'm naturally gravitated to U because V is a natural variable of U. Now I'm talking about pressure. U does not have pressure as a natural variable, but what does? Right. It's obviously what he's trying to get to. So, and this gets the symbol, the Joule-Thomson coefficient, just done this way. Okay. Who cares? You'll never see that from me again, but again, I don't know what's on your MCAS and GREs. Okay, so they build a device. Actually, kind of a lot easier. It is adiabatic, and not so bad at drawing. I don't think I would do too well today. And it's in the adiabatic cylinder. Oh, sorry, I screwed up. Put my way. Okay, now there's a funny thing about this. This does, I always have a pain drawing this kind of thing. Okay, there's a plunger, or ubiquitous plunger, in the magic cylinder. There's this chip in between, and on the other side is another plunger. Like this. And you got one guy on one side pulling, and the other guy on the other side pushing. Okay, so this let me point out that we're going to be at P1, B1, T1. And then what I would actually do is initially I'd have this plunger pressed against here, and you're going to go eventually to P2, B2, T2. Okay, and this is a zeolite. Okay, I can't write this down because it's too hard, but basically, okay, now again, remember we're going to start this adiabatic for obvious reasons. You want U to be 0 for H to be 0, and I'll prove to you how H is 0. So that's what I'm going to do right now. Before it wasn't hard to prove that U was 0. Oh, I erased it. It wasn't hard to prove that U was 0. This one is hard to prove that H is 0 in this device. Now, again, the way this is going to work is you're going to have a certain volume, and of course a certain temperature, by room temperature, pressure, probably 1 atm, and then you're going to have this guy actually closed up, abutted to this thing. And I'm going to explain this thing here in a second. You're going to have it punched up to this thing, and what you're going to do is you're going to apply constant pressure on the left and let the gas seep through this zeolite thing. And what this is an inorganic, it's like a ceramic, but it's got a lot of really tiny holes in it. Now that means it's going to let gas pass, but it kind of randomizes the gas motion coming through, so there's not really any work. Right? Remember that work is coherent motion of gas, and when I'm pushing something out of the way, I'm giving them a coherent direction, but I'm actually not in this case because the zeolite with this weird channels all inside of it, it makes the gas move all kinds of random different ways. And so with this thing, with these tiny holes, you can imagine that I can apply, let's say, 2 atmospheres on this side, 2 atmospheres of pressure, and I can hold that 2 atmospheres pressure because the gas is seeping through. So I have an escape route. So I can constantly, normally, now of course, remember, this is the end of the cylinder. If I apply 2 atmospheres of pressure, I'm going to go from 1 to 2 atmospheres of pressure. And then, of course, the plunger stops because I've equalized pressure. Right. Yeah, if I add 2 atmospheres of force out here, once the pressure builds to 2 atmospheres, then my motion stops. I'm not strong enough to go further. That won't happen. I will maintain 2 atmospheres of pressure all the way until the plunger has come to the zeolite stop. and it will never have increased beyond 2. Now here, a guy is pulling. The guy is pulling with minus half an atmosphere, so I've got 2 atmospheres pressure, half an atmosphere here, so he's going to pull, right, until I'm done, and he's pulling with half an atmosphere, so when this pressure is always at half an atmosphere, and then you stop, and you measure the temperature. So you kind of get that. It's a funky device. It's a very odd device, but it's not too bad. Again, it's different than your traditional plunger because I can empty the magic cylinder. Normally I can't. Of course I can. It's made of metal, but this one isn't. So it has a leak, and I can maintain 2 pressures constantly. That's the whole idea. If that's still kind of confusing, I wouldn't be surprised if it was. I'm sorry about that. Let's do it mathematically. Let's see. Okay, adiabatic, change in work, change in heat, sorry, is 0, and therefore the change in U is the change in work. And I've got 2 sides doing work. I've got expansion, I've got contraction. That's work. So I know that U, the change in U will be this change in this work, and I have to get to the change in U to get to the change in H. It should have been 0. I must calculate this, and this is my only way. You know, I've got 2 sides. It's to the left, and this is a compression against constant. Remember, I just made a big deal of this. What's held constant here? Pressure. It's a compression against constant pressure. So work then is going to be, okay, I've always got minus PV. Exterior, but now that's going to be P1, and I'm going to go from V1 to 0. Okay, and so that is minus P1. All right. So again, I can maintain this pressure at P1. In my example, it happens to be 2 atmospheres, whatever. So then I know that I have upper limit minus lower limit. So this ends up being P1, V1. Okay, right? It's very simple. I'll barely write anything. And the funny thing about this one is that you initially start at 0 volume and you end up at V2. And I'm not going to worry about the exterior pressure. The P2 is the exterior pressure. That's why it expanded. This is going to be minus P2, V2. And I'm not going to do the math. It's child's play, right? Okay, there we go. Now, let's do the change in U. Change in U. Now, remember, this guy expanded is the final state, and that guy with its volume. Initially, there was nothing here, so the initial state was here, and finally, nothing's in here. The thing is squashed, and everything's in here. So this is going to be U2 minus U1. And here, I should have done this. Sorry. Sorry, I should have done that. Now, to do this, because of work's path independence, the only change in U is the change in work. I just said that. I just said that right here. So you add them up. Just add work together. If they happen to be positive or negative, that's not your business. UPAC decided what was positive and negative. You didn't. So I know I'm just going to add them up together because energy's add and work is energy. If they choose to be positive or negative, that's their choice. Okay, so this ends up being U2 minus, sorry. My bad. My brain just kind of screwed up there for 1 second. Okay, I've just added them together. This one happened to be negative, but that was its choice. Okay, now let's bring this guy over here. U2 plus P2, V2 is equal to U1 plus P1, V1. Okay, what's U plus PV? H2 is equal to H1. And therefore, delta H is here. There we go. Okay, so, sorry, next, oh God, I'm sorry. We're trying to have to get your homework back. We'll do this bit for this guy here next time. Sorry about that. Here's your homeworks.